Hello there. First of all, quick shout out to Brendan. There are a couple mistakes in an original version of this video about writing derivatives, and he spotted them all. So there were two of them, and he got them. So cheers, Brendan. I'm remaking this video, and it's about writing derivatives. So we're going to explore, and this is for learning intention number. What number learning intention? Is this number 8? And I think I even wrote number 9 in the previous one. So this is for learning intention 8. We're going to learn how to write 6 basic derivatives, but it's going to get tricky pretty quickly because I'm also going to talk about the derivative operator as a linear operator. So that will make sense in a moment. But first and foremost, I want to talk about notation. Notation is how we write these things. So you'll remember from last year what a derivative looks like. If I have the function y equals x squared, the derivative of that can be denoted dy dx, and the derivative of x squared is 2x. So if you ever meet someone who's really old school, they might say this as dy by dx, but these days people say dy dx. So if y equals x squared, dy dx equals 2x. But there's also functional notation. So you can have f of x equals x squared, and the derivative is noted f dash of x, and that's going to equal 2x. The reason for the difference is historical. So different mathematicians use different notation, and they didn't realize they were talking about the same thing at the time. This was made popular by the mathematician Euler. I forgot where this comes from. Lastly, you can think of the derivative as an operator. So an operator is something that does something. So if I have 1 plus 1 equals 2, the operator is the plus symbol because it operates, it changes things. So if plus is an operator, this is the derivative operator, and you can operate on what's in the brackets. So I can put x squared in here, and this is saying d dx of x squared equals 2x. So this is operating on x squared. Another way to think about it is it's kind of like, this notation is kind of like if you subbed in x squared, because y equals x squared, into here. You would get this notation. Can you see that? Because the y gets replaced by the x squared. So now that we've gone over notation, I'm going to be mixing up my notations to keep you on your feet. Now we're going to go through a bunch of derivatives you need to know for this year. So I'm going to do the basic one, then I'm going to do an example, then I'm going to give you the formula. So we'll start with the exponential function. It's probably the best one. So if you have y equals e to the x, its derivative dy dx equals, brace yourself, e to the x. It is its own derivative, which is a very important and interesting property that gets used everywhere. Very important, this function, and the fact that it's its own derivative. So let's do, I'm going to give you the more like kind of trickier formula. So this is this is the most basic one. So the formula for finding the derivative looks something like this. If you have y equals e to the power of some function, then the way you find the derivative is by taking the derivative of that function up here and popping it out the front. So f dash of x e f of x. Alright, so that would look a bit obscure, but if you look here, it kind of makes sense, because x is the function up here. The derivative of x with respect to x is 1, so 1 pops out the front. So that kind of makes sense for this, but I'll give you an example. So let's have a look at an example of this. Suppose that y equals e to the power of x squared minus 6x. Well, the derivative of that equals, well, you take the derivative of this, which is 2x minus 6, and you pop it out the front, and then you just write the rest. And that's your answer. So take the derivative of the exponent part, chuck it out the front, and that's your answer. That's how you find the derivative there. Alright, let's move to our next function, which is the natural log function. Natural log, the natural logarithm. So if you have y equals the natural log of x, its derivative, and this is not at all obvious, is 1 on x. If you want any of these proved, it's not on the course, but if you want to sit down and find out why all this is true, I'm more than happy to. Just track me down and say, hey, I want to know how this actually happens. But you don't need to know it for the course. It's not on the course. You just need to memorize them. You do not need to know how they come about. You need to memorize them though. So there's the derivative. So the formula, it looks something like this. If I have y equals the natural log of some function of x, then the derivative equals f dash of x over f of x. I'm going to do an example and then I'm going to explain to you how I remember this fact. Let's do an example. So if I have y equals the natural log of, let's choose something different. I don't know, 2x minus a half x squared. Well, its derivative is going to equal, well, it's the derivative of f of x. This is f of x, so it's the derivative of that, which is 2 minus x over that original function, 2x minus a half x squared, like that, and that's your answer. So the way I like to remember this, every time I do this I say something in my head, and that thing I say in my head is, I don't think about this formula like this, I think about it like diff over original. That's what I say when I do this process. I say take the derivative and chuck it over the original. So here I take the derivative of that and divide it by the original. You do need to know this formula. This is how I remember it. Diff over original. So I'm going to throw these in whenever I use them, just to let you know, because I find them useful and perhaps you will too. So that's the natural log function. Let's move to our trig functions. Let's move to the sine function. Sine function. This is actually how sine is spelt. It's just SIN for short. So that's actually how sine spelled. Sine, so if y equals sine of x, the derivative, this is quite nice, this one, is cos of x. Hey, one that kind of seems nice. Let's do the formula. So more formally, if I have y equals sine of some function of x, the derivative equals, you take the diff of that, the derivative of that, I say diff for short, chuck it out the front, put a cos there, and leave the original function there. Let's do an example. Example 3, let's say y equals the sine of x cubed on 2 minus 3x squared plus 1. Well, the derivative of that equals, well, we bring the power down, subtract 1 from the power, so we've got 3 x squared on 2 minus 6x, and 1 goes away, so that sits out the front here, and then you just write cos and that function. And that's your answer. Looks complicated, but it's actually not too bad. And then let's meet the cosine function. I know this is thrilling. Look, you just have to memorize these. These will definitely be on the exam. They always put derivatives on. So y equals cos of x. The derivative is negative sine of x. So sine diffs to cos, cos diffs to negative sine. Let's look at the formula. So the formula for that is, if I have y equals cos of some function of x, well, the derivative equals negative, chuck the derivative out the front, sine f of x. And let's top it off with an example. Let's do y equals cos negative x to the 7. Well, the derivative equals, it's going to have a negative out the front. The derivative of that is negative 7x to the power of 6 sine, and that stuff in there. If I'm going too fast, pause the video. And if we tidy that up, negative times a negative is going to make a positive, so that becomes 7x to the 6 sine negative x to the power of 7. There's a property which you can use here, this negative for sine, and this only works for the sine function, and yeah, it pops out the front, so you can rewrite this like that if you like. Also works for the tan function if you remember your trigonometric identities. So if you want to be really clever, and they might put that on the multiple choice to try to trip you up, that's something you can do. So we've done sine, cos, e to the x, natural log. What could be next? Yeah, you guessed it, it's tan function. The tangent function. Tan is short for tangent, and a tangent line is a line that just touches a curve. So it's like, it's actually the same word origin as the word tango. So let's look at the tangent function. Because like tango, you know, you get close. Tangent lines get close. Tangent function. If you have y equals tan of x, I know I'm full of useless information. The derivative is, and this is not at all obvious, 1 on cos squared x. Remembering that little squared there means take cos of x and then square the quantity. Another way to write this is using the secant function. So another way you'll see this written is sec squared x. So in other words, sec of x, the secant of x, is actually 1 on cos of x. This is the only reciprocal trigonometric function you need to know, and it only pops up here in methods. If you're doing a specialist, you will need to know the 3 reciprocal functions as well. There's sec, cosec, and cot. But for now, we only need to know sec, and you really only need to know it for the tan function. It doesn't really come up anywhere else. Well, let's see. Let's look at the formula for this. It's the same sort of story with the formula. If you have y equals tan of some function, then the derivative is, I'll write it in 2 ways. It's this, or it can be written with the sec squared notation. So look, you basically chuck the derivative out the front. And I will definitely do an example. Let's do y equals, no, I need to use a different notation. Let's do d dx of tan tan 3x to the power of 4. Well, that derivative equals the derivative of that, which is 12x cubed, divided by cos squared of 3x to the power of 4. Or you could write it like this, so you could also see it written, and this is important for multiple choice, you could see it written like that as well. That's another appropriate answer. Alright, so those are all the basic derivatives you need to know for all of methods. But I want to show you, I want to do an example of one we were struggling on last year, and I want to do an example of how the derivative operator is a linear operator. So if you permit me to do 2 more examples, I'll be very grateful, and this is for learning attention 8. So I'll give you another example, example 6. So we got stuck last year on finding the derivative of root x. And I think the reason for that was you had to use some index laws. Here's how you find the derivative. Square root is the same as raising to the power of a half. So the derivative equals bring the power down, subtract 1 from the power. Now we like to rewrite things with a positive index. So this jumps down the bottom and it has a positive index. Finally, we like to rewrite it with the square root symbol. So there you are. That's how that becomes that's its derivative. So you know what? Memorize those steps because it's very common that pops up. Make sure you're comfortable with that. Learn that procedure. It's an important procedure to know. Finally, I just want to do a hideous derivative example just to show you how you can combine them all. So let's say we have the function y equals sine of x plus e to the x squared minus cos of x cubed. Look at that, that's terrible. Well, the linearity property of the derivative says, well, you just find the derivative of each part. So although it looks hideous, you can do it fine. Diff of sine of x is cos of x. Decided to put it in brackets that time for no good reason. The diff of that is 2x e to the power of x squared minus, well, cos diffs to negative sine, and I'm going to put that derivative out the front. So there's a negative sign just there, and there's going to be another negative sign because cos diffs to negative. So we're going to put a negative 3x squared, because remember cos diffs to negative sine x cubed. Alright, so I've taken the derivative of that, put it out the front, and I've got the negative sign there as well. Look back at the derivative of cos if you're confused where that comes from. But then tidy it up. Cos of x plus 2x e to the x squared plus 3x squared sine of x cubed. If you're comfortable with that, you're doing very, very well. If you're comfortable with that last problem, you should be very happy with yourself. And if you have been, thank you for watching.